everybody, Norm here, coming to you from a slightly different venue of questionable value and questionable safety, but I'm going to give it a shot anyways, because I want to get these out the door, and sometimes it just takes longer than I want. And you know what, this time I think I have remembered it, because I just spent the greater part of 45 minutes trying to solve challenge 3 in the Euler project, and we're going to see if I can recall and basically over narrate, even though I'm not watching the video, exactly what happened. So, well, some of the things that came out of this while working on the problem was, once again, I don't know math. Or I don't know the typical stuff that a typical mathematician or somebody who's classically trained or did well in their math classes in college would remember. And so this question that you can see here is basically asking, what is the prime factorization? Now, that's a phrase that I've never heard before. I know prime numbers. I kind of understand what a factor is, but the idea of prime factorization was not what I was able to easily take in. So it quickly led me down this path of, I need to understand something about what those numbers are. So, but you know what? I know that LabVIEW already has a lot of built-in functions. And although I am more akin to recommending that you learn the palettes, you learn the functions that are there, there's a lot of math that a lot doesn't exist up in my brain. So I decided to go the route of just searching. So you can see here that I just went not for quick drop, because although quick drop can take you to let you know is there a specific function that you know, that is not the home that you should go to figure out where that function is. So I can leverage quick drop up front, but what I need to do is go ahead and leverage the search within the palettes to find out what effective function that might talk about primes or have things nearby. And so you can see just by simply typing in prime, there's a pretty limited number of options that show up there, one of which I know is going to be valuable in this entire escapade for problem 3 is prime. So it's going to allow me to do a test of a number if it's prime. I don't know how it does that, but I'm grateful that it's there. And then you can see very quickly prime factorization, or factor all prime numbers. That might be exactly what we need. And in fact, as you can very quickly see here, I go ahead and I take the number, I put it on the diagram, and voila, I put it in, and I get all prime factors. And when I do that, I can also go ahead and test against it, and boom, right there, the fastest possible answer. I have one function, I can get my prime factors, and that tells me what I want. Now, is this cheating, or is this leveraging the tool that's in front of you? Well, I will continue to lean back onto what LabVIEW stands for: Laboratory Virtual Instrument Engineering Workbench. And this is just one of the tools, which is a dense math library that works not only on the host, but on real-time targets and on multiple platforms that you didn't have to go out and get. So, indeed, to some degree, I'm not going to say it's cheating. However, I think it's probably against the spirit of the challenge at hand to figure out what is actually what are you trying to learn by doing this. Now, indeed, I just learned something about LabVIEW. It has a bunch of prime factors. They exist underneath this elementary mathematical functions palette, and that's very, very useful. However, there's also hey, how does math work in general? And so what I needed to do is, hey, let's go through this same process, but instead of just taking a function that gives me the answer very specifically, let's go through and dive into figuring out, hey, if I could, as a minimum, the only thing I had was the ability to figure out prime numbers, where would I go and what would I do? All right, so after a bit of digging, I kind of was able to understand just a little bit of prime factorization, and I was able to get through the process of seeing that you take a number and you divide it by a prime number. And if that gives you a whole number, then you continue to divide it by that remainder, basically whatever, once again, the whole part that is left, the quotient in this case, and you continue to try that again, dividing that by more prime numbers, starting at the lowest number. And every time that you have a whole factor, effectively, you tick that number off and you once again, log that was the factor of it, and you continue to just go. And as I looked through all of these videos, I very quickly, it took me a minute to figure out, like, that's all that we're looking for in this prime factorization. Just basically keep dividing by 2 until you can't divide by 2 no more, and then you divide by 3, and then 5, and 7, and on and on and on, in hopes that what you're finding is a prime factor of whatever's left over in the overall system. And so what they were looking for was not the full prime factorization and kind of clumping the numbers together. As you can see, like the number of the square of 444 is 2, 2, 2, 2, 2, 3, 37, 37 or something like that, right? And what I was able to figure out is just, okay, let's go through and I was going to try to, for each new quotient, calculate the prime numbers again and again and again. And I realized that figuring that out was slowing me down. And that's such a big part of any time that you're doing these programs and you're trying to figure something out, whether or not it's just for the Euler project or you're figuring it out from scratch. Sometimes going the inelegant route might be just necessary so that you can figure out, can you even get to the get to what's needed in the first place. So what did I decide to do? Well, I did cheat a little bit, and I was able to figure out that there was a limitation that your prime factors are always going to be less than the square root of the number that you're trying to figure out the prime factor for. And that makes sense because once you hit that point, one number is going up and the other one's coming down. So none of them are going to be greater than that. So I just collected all prime numbers that indeed are less than the square root of whatever number we're evaluating. So now I've kind of got a bit of a database that I don't feel beholden to calculate each time. And then I start to reference that database over and over again, and that worked out pretty well.
Hey everybody, Norm here. Sorry to interrupt, but not sorry to interrupt. Things were going along, and I wanted to just get to the real meat of some of the key features that this approach of going, recording, and then doing didn't work. So let's dive into these few things that really jumped out to me. So one of the things that really jumped out was this ability right here, where if, once again, as I was mentioning, if I turned on execution highlighting to watch my program run, this thing runs like 64,000 times in order for me to kind of watch this section of the code run. There's a great little feature. If I can get it, and it shows right here, toggle execution highlighting. You can see it right there. It is indeed a custom probe. And if you set that probe on there, you will find that all of a sudden your program runs up to that point with no problems. And then highlighting turns on. So let's see, will that happen right here? So I'm going to go ahead and custom probe, conditional highlighting. You're going to see this kind of a basic new setting of what it's going to set the next time or what it is currently. Don't care about that. But now if I just run my program, you're going to see real quickly, everything ran up to that point, and now it's going through and doing the execution highlighting. That was really handy. And then of course, it's just toggling it on or off. The other thing that's really nice too is that if you need a little bit more time to watch the wires run, there's a new feature up here that allows us to go ahead and indeed set the speed at which execution highlighting happens. You have to hold down on the little light bulb a little bit longer and it drops down. But that's another great thing that I used while doing this, because I was trying to watch these values move and I needed, once again, my brain's just spinning at whatever rate it was. And so I had to slow it down on a couple different instances. So once again, two different features that we've caught right there. Some of the other ones that I used from the previous ones were indeed the conditional indexing of those to kind of conditionally build up that list of available primes that were in there. And something else that is part of this, which is really, really helpful, is on a for loop, as you can see. Let me zoom out a little bit there. The for loop, I can conditionally exit out of the for loop or only run the for loop, in this case, while a value is true. And so I was able to use the logic of the remainder quotient to say, hey, keep going through this for loop until you find something that has no remainders, thus declaring that the incoming value is actually a multiple of that specific prime number that we were looking at there. And so that allowed me to not have to have an extra, what's the word I'm looking at, not going through the logic, because normally when you turn on the conditional, it's a stop condition. When value true, then you stop. And so it was able to take advantage of that here. And then in the math of everything once again, I'm kind of short circuiting some of the conversation I had previously is, well, the way that this works is that it takes in whatever the value is here, and then it goes through one at a time, each one of the prime values that you have. It's like, all right, is this value a prime number, or is the number that we have in perfectly divisible by that prime number? No, then go to the next prime number, then go to the next prime number, and then go to the next prime number. So starting at 2, 3, 5, and so on and up from there for all the primes. And at some point in time, you will find the prime factor that will work. So honestly, I've actually forgotten a little bit about how this goes. And so what I'm going to do actually is go through and look at and see what happens when we have this work. But another feature that I was able to use within LabVIEW in this case was a great little feature of, hey, I don't want to watch this run every single time for each one of those primes, 3, 3, 7, right? There's a lot of numbers here. If you can kind of see, like I'm up in like to the 11th power of a number here trying to find stuff. So that's not going to work out for me. But what I can do, another great conditional feature on the probing system, I'll let that go ahead and run for a moment, is if I right click and I custom probe, I can also have a conditional. So that is another great feature, is that I can now let this whole program run as it iterates up and up and up. But now I want to only stop the program and watch what happens when that condition is met. So I'm going to, when it's false, that's how it's going to go ahead and stop. So let's go ahead and right click, custom probe, and then I'm going to go to conditional Boolean, and now I will expand this over here and change my condition to be and I want to pause when that condition is false. I will now turn off execution highlighting, and boom, now it got to the end of that iteration, and now I can go through and now I can turn on the rest of my highlighting of my debugging to go through and watch it run. So now you should be able to see, if I go ahead and I zoom in to get this proper here, now I'll go through. Now you can see, hey, we've run that through. We have found our singular whatever that specific index is. Now it's gone through. I'll turn that execution highlighting off again, and you'll see that it's going through and it's running up until that point where it has met it. And now I can even watch it go a little bit slower, because once again, maybe I didn't catch everything that happened in terms of the values of the shift registers and everything else. So once again, it's that different feature of the conditional. Okay, so there's the value. Okay, then it took the old value, moved it around. It has the original prime. I'm going to go ahead and let that go. It starts over at 2. And of course, then we end up with all these iterations that don't quite work as we go through and we index up each one of those prime factors, searching for the right one to find out where it eventually comes through here. And that value, that remainder value, comes out as 0. So once again, that other feature that we have that's particularly valuable in the conditional highlighting. Let's see. And then the other thing that's probably just worth noting here is the style that I'm picking up that you can possibly do as well, where with my for loops, I like to turn the labels on in my while loops as well. And I like that to be my documentation for the for loop. It describes for each prime, right? And then what are you going to do in that for loop and kind of that condition.
All right, so I hope that gives you a good insight towards what you're getting from LabVIEW and Euler Project 3. Not only do we have an entire function that just gives us what we're looking for, but also we can go through and manually multiply that and figure that out. And I could have probably pulled the math from the, hey, get all integers in, but for now we're going to go ahead and leave it as simple as what we've got. If you want to go ahead and do it, leave your notes in the description below and put a post, put a link, put it somewhere where we can go ahead and dive into this specific problem and see how you solved the Euler Project Problem 3. Thanks.